I'm Felix. I'm a second year CSE student and I want to share with you how to code golf an ELF executable. Now, for those of you who don't know, an ELF executable is basically it's your standard binary executable on Linux, which is roughly equivalent to any exe file on Windows. And code golfing is the act of creating a program that contains the smallest possible amount of bytes. Now, what we're going to do is go on a mad quest to create the smallest possible executable. And obviously the first thing that you need to create an executable is a compiler. So first of all, I'm going to introduce you to a tool that you may or may not have used called GCC, or the GNU-C compiler. It's mostly used to compile C code into an ELF executable, which you can actually run on your computer. One thing it uses to do this is libc, which is the C standard library, which amongst other things contains functions which allows your C programs to make system calls to the kernel. GCC also acts as a front end to the GNU linker LD, which takes bytecode object files and actually turns them into an executable. So what this means is that GCC itself can take a file containing C code or a bytecode object file, which I'll explain a little bit more about later, generated by another program such as an assembler. It will take these files and transform them into other object files, which it then passes onto the linker, which then stitches together the bytecode into an executable. So if we go back to code golfing, if we want to create the smallest possible executable, then we need to set ourselves a goal. And about the simplest program that you can possibly get is one that just returns a 1 or a 0 or some other number. In Unix, there are already programs in your terminal that return 0 and 1, and so I thought it would be a bit boring to do that. So why don't we create a program that returns the number 2, the next logical step. So yeah, let's go on that mad quest. So this is our base C program. All it does is return the number 2 with no operands, and that is about as simple as you can get. So here we have it. And if we want to compile that, I've just got this little script which will compile it and print out what it returns and then show us how big the file is. So if I run that, we can see that yes, it does indeed return the number 2, and it is about 15,896 kilobytes. And then you might be bytes. You might be thinking to yourself, that's a very, very small file. It's about as good as you can get. But no, it is not. It is way too bad. Why do we need that many bytes to just return the number 2? It is outrageous, in my opinion. So, there are some ways that we can improve this. If we, for example, pass some extra GCC flags, so we have -s, which can strip unnecessary headers off of the file, and we also have -03, which will optimize the executable in certain ways. So if we go ahead and do that, got this script here which has these different things passed in. And if we run that, we see that instead of having 15k bytes, we have 14,264, which is a little bit better, but you know, there's still a lot of room for improvement, I feel. So we've got to start thinking out of the box a little bit. So how about we stop using C altogether? Now, I chose C just because GCC, I know a bit about that toolpath. A lot of people know about that. It goes straight to linker. It's very easy to compile using it. But one thing that isn't often talked about with GCC is that you don't actually have to use C to compile something using GCC. So if we start coding an assembly, but still using libc functions, but we're coding in assembly but just using those functions, hopefully that should save some overhead in theory. So what we have is this assembly file, like I showed on the slide. We have this entry point main, which is defined in libc. It's essentially the same as this entry point in main, except it's just in assembly, of course. All this program does is loads the number 2 into this register RAX and returns it. Return is again a libc function. So if we want to run that, which we can do like so, we're going to use the net-wide assembly thing, whatever that stands for, to assemble our assembly code using GCC. And if we do that, we find that we actually have no improvement whatsoever. which is probably fairly confusing until we realise that last time we used the -03 improvement for GCC, and all that does is basically compile it down to, it optimises it such that it's as good as this assembly code can be. So, we've got to get a bit more extreme here. What is holding us back? And the thing that's holding us back is libc. Of course, it's very hard to create a program without libc nowadays, given that you need it to start a program with the main function, and you need it to end a program with the ret function. But there are ways of doing it without libc. Instead, we do it with kernel calls. Let me just show you this program in advance. So instead of using the entry point as we did last time, we use _start, which is the name of LD, the linker for GCC's default entry point. GCC itself actually calls start without an underscore by default, which then calls _start. So let's just cut that out. RAX we are going to fill with the system call ID for exit as defined in the Linux kernel documentation, and RBX is going to store the parameter that we actually want to return. So what happens when we call this int ox80 is we are saying to the Linux kernel, yes, I would like you to do the thing with ID1, which is return, and I want you to use this operand that's in RBX too. So what it will do is it will return 2, fairly simple. So yeah, let's actually do that. And what we get is, let me just check I'm running the right file. Yes. What we get is this, which is again slightly smaller, just marginally, another 100 kilobytes or so. Which makes sense. We've removed a bit of that overhead, but 13 kilobytes is still way too much, in my opinion. We can go a lot further. So we can do a couple of things. First of all, we can stop using 64-bit registers. So if I show you this new assembly program, before we were using RAX and RBX as our registers. We're going to change them to AL and BL, which are the 8-bit versions. So essentially, it's just the first 8 bits of those registers. Bit easier, bit less overhead, surely, to write to them because you don't need to write a load of unnecessary zeros. And just to reduce overhead even more, instead of moving the value 1 into AL, we're instead going to set it to 0 by XORing it with itself and then incrementing it, which should reduce the need to have the number 1 hard-coded into the file. And then we return just like usual. Yeah, that's our program. The other thing we can do is actually stop using GCC, because like I described earlier, we have this toolchain within GCC. There are 2 components, the compiler and the linker. Now that we're not using libc at all, and we're just using these kernel calls to start and end our program, we don't need to use GCC, we can just go straight to the linker, because we're not linking in, we're not using GCC to link in libc at all. So what we can do is call that, let me just make sure I've got the right one again. Yep. If we call that, we see a massive improvement going from 13 kilobytes to 4 kilobytes, which is just so much better. And the main reason for that is just not using GCC. GCC itself introduces a lot of overhead that we just don't need. So we've managed to cut that out. What's the next thing we can do though? Because 4 kilobytes is still quite a lot. And in fact, if we look at, I should have showed you this first. If we look at our output file, a.out here, we can see that we have a lot of just 0 padding space here. We have a lot of 0 padding space, which is just completely unnecessary. The actual, we have a header here, an elf header, and we have some stuff going on down here. It looks like a bit of metadata that's been put in by the linker. We want to get rid of that, but obviously we can't just go in and backspace it all. Everything would complain. So how can we do that? Well, we can remove something called the section header table, which is something that's retained by LD when we pass it to the linker. In order to understand this a bit better, I'm going to introduce you a little bit to the structure of the ELF file itself that we're creating. So, in short, ELF files can have 2 different types of header. We have the program header table and the section header table. ELF files, the object file that we passed to the linker in the first place is basically a very similar format to the ELF, except it's not actually executable, it's just a lot of things in place ready to be linked together. When we're doing the linking, we strictly need this section header table. It's very important for the linking process, but it is not needed at all during execution. So what if we manually created our own ELF file with no section header table, but we need to retain this program header table for actually executing it. This would, in theory, cut out the compiler and the linker completely. We're going straight from writing assembly to just a binary file. So yeah, we can do that. It's a lot more work than the previous steps, but this is our new assembly file. It is mostly ripped straight from the ELF documentation, which was all originally in 32-bit, so I had a fun time trying to get it to work in 64-bit. But I don't really understand it fully, but you instantiate some header values here and here to use in the actual header during the execution, and we have our assembly code down here that we are running in the first place. So let's try and compile that, see if it works. Fun times. Let me just try. Yeah, this is our file again. This is what we want to run. And what we can see is we've gone from 4,320 bytes all the way down to, I don't know what happened here with the permission, but 128 bytes, which, well, you saw how many zeros there were last time. What we can say now is that every single byte in this assembly code, we haven't done it quite in the same way. We've got a bin output format instead of L64, so it's not really doing any processing, it's just turning it into a binary file and outputting it. But we know now that every single bit in this file has been accounted for and is used. There is still some zero padding just because the ELF specification itself says that there has to be certain data within the file that is aligned to certain parts, but about the smallest we can get is 128 bytes, and I think we've done a pretty good job here. Now that is as good as I have managed to get. This is just the file again, for you to gaze upon its majesty. This is about as good as I've managed to get in 64-bit. Now, there have been people online that have managed with 16-bit compilers or 32-bit compilers to do something that I can do in theory, which is, when we were talking about earlier, in the loadable file, we still have an ELF header, we still have a program header table. What we can do is we can actually, against the ELF specification technically, but Linux will still run it, we can move that program header table into the ELF table where we have lots of zero padding, and those zeros are never really read, they're just used as padding. So we can move that program header table inside the ELF header, and if we can get the bits just right, it should, in theory, still run. But I simply don't have enough time to do that, or the dedication, or the patience. If you would like to do that, by all means, do. Give me a DM if you've got, if you want to know any more, find some of the resources that I use for this. There's my website and my Discord. Any questions?